The Taurus Report is the bull in the china shop of cosmology. This week I am going to propose an experiment that will disprove general relativity. I must apologize. I was out last week, sick, I think with the newest iteration of COVID. I didn't bother to get tested. I've had COVID several times now. But it really had me down and out. I was not able to talk without coughing. So skipped last week, but we're back this week and we will continue. So this week we're going to take a look at a practical experiment that will disprove general relativity or else disprove CGC, cyclic gravity and cosmology, or potentially disprove both of them. And it is based on this idea I've discussed quite a bit in various videos, past videos of the Taurus Report. It is based on this assumption about cold neutrinos. When I use the word cold, I just mean that the neutrinos are not moving fast, and with current technology, the only types of neutrinos that we can detect are hot neutrinos, neutrinos moving very fast. But as you know, CGC assumes that cold neutrinos are attracted to masses, any massive object. They are attracted to any massive object, and they form a density gradient around that object. And CGC assumes several things about these cold neutrinos that aren't too much of a stretch of imagination, because we've seen these types of behaviors in particles in general. So it's not too much of a stretch to posit each of these things. So again, the first assumption is that cold neutrinos are attracted and congregate around masses to form a density gradient. That's the first assumption. Not too much of a stretch, I don't think. Second assumption is that these neutrinos interact weakly with light. We know that neutrinos do interact with light via the weak force. That is well known already. But it's not too much of a stretch to posit further that cold neutrinos refract light. So if you have a density gradient around a mass, there is going to be refraction of light. And so that is another one that I feel is not too much of a stretch. Then the third one is probably the one that is most challenging as far as imagination. It certainly has not been proven. I don't feel that it's too much of a stretch to me compared to positing that space itself stretches, which to me is quite a stretch, literally and figuratively. But the last assumption about neutrinos is that higher concentrations of neutrinos suppress all quantum processes. So the effect on the macro scale, what that means is that higher concentrations of neutrinos, they will slow down time. The way we would experience that on a macro level is they slow down time. So this means time is going to slow down around any source of gravity, like a massive object. Also, it means for an object traveling at high velocity at relativistic speeds, it will encounter more neutrinos as it travels, and because of that, time will also slow down for an object traveling at relativistic velocities. Now, with these three assumptions, if they happen to be true, which we don't know yet, but if they happen to be true, then we can get all of the results that are posited by general relativity about increase of mass at relativistic velocities, the bending of light around a gravitational object, time dilation around a gravitational object and at relativistic velocities. We can get all of those things without deforming space. Now, just as a quick aside, which I've mentioned before about increase of mass. So increase of mass at relativistic velocities is not related to neutrinos. That is just a consequence of the electromagnetic force. Because I'm positing that gravity is a relic of the electromagnetic force, as I've explained in previous videos, because I am positing that, then it is well known that as charges increase their velocity, the electromagnetic force increases exponentially. And so this explains, since gravity is a relic of the electromagnetic force, this explains increase of mass at relativistic velocities. So all of those things, which Einstein with his general relativity tried to explain with a new sort of space-time geometry, CGC instead explains with well-known forces and particles without having to posit any sort of non-Euclidean geometry. But let us proceed now to take a look at the the test that I am proposing, a very doable experiment that will disprove general relativity. Before drawing out the experiment, I just want to remind you of one other major difference between CGC and general relativity. And that is that CGC proposes that not all inertial reference frames are equal. In other words, CGC proposes that there is actually something that we might consider a universal rest frame, and that is the rest frame where the CMB, the cosmic microwave background radiation, is not Doppler shifted. So in other words, if you're at rest with the cosmic microwave background radiation, if you are at rest with that, in the sense that that is not Doppler shifted at all, then that is going to be the rest frame where, on average, most cold neutrinos will have the minimal velocity. So in that rest frame, time will pass quickest in that rest frame. And what do I mean by that when I say time will pass quickest? Because neutrinos inhibit quantum processes and neutrinos cause time dilation, they cause time to slow down. If an object is at rest in this universal rest frame, since that is the rest frame in which statistically most neutrinos would have the least velocity, that means an object at rest in that frame would encounter the fewest cold neutrinos if that object were assuming it's far away from any gravitational force. Because, like I said, any gravitational source will attract a concentration of cold neutrinos. So if an object is far away from any massive object and it's in empty space, and it is at rest with respect to the CMB, meaning the CMB is not Doppler shifted, that object will be encountering the fewest number of neutrinos, and the object will be at rest with respect to that universal frame. And so taking advantage of this fact is what the experiment is going to be based on. So let me draw that out here. Not being a professional astronomer, I don't know the exact direction by which the CMB is Doppler shifted, but if you Google something like rest frame of the CMB and so forth, and just kind of explore all the links in there. I found one that kind of explains it very well, and I'm sure a professional astronomer would be able to look at these directions and find what direction in the sky we would have to move in and at what velocity in order to come to rest with respect to the CMB. So with respect to the Earth, whatever the direction that is, I'm not sure what direction it is, we'd have to move like, according to this, 375 kilometers per second. We'd have to come at that velocity in the proper direction. And if we were at that velocity in the proper direction, then the CMB would not be Doppler shifted. So that's what I mean to come to rest with respect to the CMB. So let's talk about this experiment that I am proposing here. This is the experiment I am proposing. So let us suppose this is the Earth. If we were to launch a probe in precisely that direction that comes to rest with respect to the CMB, and that is at 370 kilometers per second, if we were to accelerate a probe to that velocity and hold it steady at that velocity in that proper direction, then that probe would be at rest with respect to the CMB. And I am claiming that it would have the fewest neutrino encounters possible. So what does this mean? Let's focus on this a little bit here. Let's see. There, that looks a little better. Okay, so what does that mean? So the probe at this velocity would be at rest with respect to the CMB and would be encountering the fewest quantity of neutrinos. So because it would be encountering the fewest quantity of neutrinos, then time for this probe would speed up. Time would speed up relative to Earth. Now, if we launch a probe in the exact opposite direction and at the same velocity, and then each of these probes would be sending back a signal to the Earth, like let's say a beep every couple seconds or every second. So like once per second, okay, once per second, the probe is to go beep and send a beep back to the Earth. Okay. Now let's look at this in terms of general relativity. According to general relativity, no inertial rest frame is special at all. And so for the Earth, these probes would both be moving relative to the Earth. And because they were moving relative to the Earth, according to general relativity, they would both, time would slow down for them. And so these beeps would be coming, because time slows down, we would receive them at the Earth slightly greater than 1 second. And they both would be equal. They're both traveling with the same velocity relative to the Earth. So the arrival time would be slightly greater than a second. And I do have to point out that some accommodation will have to be made because of the Doppler shift. So both of these vessels sending a signal back, the signal is going to be Doppler shifted because of their velocity. And so I'm saying that is going to have to be taken into consideration, and I'm aware of that. And so I'm not really dealing with that in this presentation, but I just want you to know that I am aware of that fact, and it would have to be accounted for. But because they're both going at exactly the same velocity in opposite directions, however you account for it, it would be the same for both. And so those signals would arrive at slightly less than 1 second. Greater than 1 second, because time would slow down for these two vehicles. Because time slows down for them, what is 1 second for them would be greater than a second for us. And so we would see these signals coming at greater than 1 second. If general relativity is correct. Now, I must make one other little caveat in that under CGC, any massive object will attract neutrinos, and that will cause time to slow down too. So we're hoping that these two probes will be launched far away from any massive object, like a planet like Jupiter, or the sun. They must be going in a direction away from the sun. And hopefully they'd both be the same distance from the sun. So any neutrino concentration caused by the sun would not interfere with the experiment, because one would assume that the concentrations caused by the sun would be about equal wherever they are. So under those assumptions that no massive object is interfering with the experiment by throwing off neutrino concentrations, what we are trying to experience is the standard neutrino concentrations in empty space far away from any massive object. That's the point. Now, let us look at this experiment. If CGC is correct, what would we see if CGC is correct? This probe, because it is coming to rest with the CMB, this one will have the least amount of, it would have the least amount of neutrinos. It would have the lowest encounters with neutrinos. Because it would have the lower encounters with neutrinos, that would mean that time would speed up for this object relative to Earth. Time would speed up relative to Earth. And so because of that, it would be slightly less than 1 second, because time is speeding up. And so the amount of time between each beat coming from this probe should be less than that coming from this probe. Now this one, because it is essentially doubling its speed with respect to the CMB, the amount of encounters with neutrinos should go up, so time should be slowed down, and so this one should be greater than 1 second. Greater than 1 second. Now, there are several things that have to be kept in mind here. Again, the Earth itself is a massive object, and it attracts neutrinos. And so because of that, there is going to be time dilation on the Earth. And when each of these probes leave the Earth, right, at first they will be encountering less neutrinos because they're away from the massive object. And so that is going to have to be accounted for too. And this is why I'm saying we should do it with 2 probes rather than just 1 probe. Because if we do it with 2 probes, then both of them will be leaving the Earth. And my point basically is this. Under general relativity, the passage of time for both of these probes should be identical. Okay, whatever it is, accounting for all the factors I've mentioned, because they are both moving with the same velocity relative to the Earth, time should pass for both of these probes in an identical way relative to the Earth, so their signals should be arriving at about the same time with the same distance in between each signal. But under CGC, this one coming to rest with the CMB should encounter less neutrinos. So because of that fact, it encounters less neutrinos. Time will speed up. And so the pulses coming from this probe should be arriving at intervals that are less. And so that is the basic idea for the experiment. And this experiment will disprove general relativity, or it will disprove CGC, or it might disprove both of them. Now, for our new viewers, I would like to remind you once again, remind everyone, how to get to our website and to see all the videos of the Torus Report in order. So if in a Google search, if you were to type in Torus Report, all as one word.com, so Torus Report is one word.com, and press enter, then that will bring you to our website. And if you scroll down, there's a few things you'll see here. First, I'd like to show you can listen to us on Spotify, but at YouTube, you will be able to go here and you will see all the episodes of the Torus Report in order, starting at the very beginning. And so you can access the reports in order that explain cyclic gravity and cosmology from start to finish. Then also here, if you click on this paper CGC, you will be able to download a copy of my paper. It's 23 pages, and it explains cyclic gravity and cosmology from start to finish, and explains how general relativity can be adapted in such a way that we do not need the stretching of space. We do not need space deformation at all. And so you can go there and see that. Now, I would like to address next, just in general, the state of cosmology in general, and to make an appeal to the professionals, cosmologists here next. So let us talk a little bit about the state of cosmology. Here is the difficulty I have. When Einstein put forward his general relativity, there is very, very good reason why everyone sort of suspended disbelief and went with it. And the obvious reason is that it made valid predictions. And it still does to this day. It makes valid predictions about the deflection of light. It makes valid predictions about time dilation. It makes valid predictions about increase of mass at relativistic velocities. So, when you're doing so well, predicting things that no one else could explain or predict, then it makes perfect sense that everyone sort of signed onto it at the beginning, even if as I've demonstrated, there are certain logical contradictions when you're talking about the stretching of space, and I've explained that in several videos prior to this. And so it makes sense to me that everyone suspended disbelief and went with it. It also makes sense in the sense that even if you don't believe it's a good explanation for what's really going on, it makes perfect sense that you're still going to use the equations when you are, doing things like analyzing trajectories or making predictions about radioactive decay at relativistic velocities and so on and so forth. It makes sense to me that the equations are used. There's a good reason for that. Now, with that said, there's an aspect in which I think modern cosmology has gone off the deep end. And that is just in the failure to recognize the fact that if we use Einstein's method to stretch space at will, compress space at will, if we're going to do that, then we come up with theories involving dark matter and dark energy that simply cannot be falsified, because after all, what is physics? Physics in general, in a classical sense, it has to do with looking at objects and defining energy in the terms of masses and velocities. Okay? So if you have some sort of, and I'm going to call it magic, and I'm using that in a derogatory sense, and that is intentional, I'm sorry. So if you have something like in galactic rotation rates where you need an attraction by magic, then you can just insert some imaginary particle, and I'll call it a magical particle, dark matter, and say, okay, because I absolutely refuse to question general relativity, and I just refuse to question it, then there must be masses that we cannot detect. There must be magical masses. Now, if you're allowed to put magical masses anywhere you need, at whatever quantities and densities you need, then you can create attractions wherever you need them. Okay? Now, with expansion, cosmological expansion, sure, Einstein, he threw in an arbitrary constant to say the universe is expanding, and that's why it all doesn't just collapse in on itself. But there's no explanation of why it's expanding. We just say it's a negative vacuum pressure. That's just a fancy way of saying I want it to expand here. Okay? So you could use fancy words, but you're just totally being arbitrary. And not only that, but what is really ridiculous is that you go ahead, and when I say you, I'm talking about standard cosmology now. So I'm sort of accusing the whole genre. So when you need a different expansion rate, like we needed inflation to explain why everything is evenly distributed all throughout the universe, so there we needed a different expansion rate. And that's all it is. It's just a fancy way of saying, okay, right here in this era, I need a different expansion rate. And man, what an expansion rate. I mean, it's expanding faster than the speed of light. And there's no explanation for that. It's just saying, oh, well, we need it. And so we just simply declare things expanded that fast at that time. Totally arbitrary. Okay? And then for later expansion, you have a different rate. Now, why does it change rates? Why does it do this? Who knows why? It's just the theory needs it. We say that absolutely general relativity must be correct. Therefore, we need this. Therefore, it's a fact. This is ridiculous. It is ridiculous. And now with the recent Hubble tension, they might be introducing, I forget what they call it, some sort of dynamic expansion. I forget the exact term that's coming into fashion now, the latest fad, where we might have even more adjustments, where we have even more eras of expansion. But really, for those of you who are laymen and skeptical as I am, as I said, classical physics, right? Classical physics is just about masses and velocities and defining energy like that. Oh, sure, you have, with electromagnetism, you have different particles, positive and negative. So you have the potential for pushes as well as pulls, depending on charge distribution. But classical physics is really just all about that, right? It's just about velocities and forces and masses. Now, if you can insert masses wherever you wish, wherever you need them, dark matter, okay? You just insert it. If you can do a pull wherever you happen to need it, if you can do a push whenever you need it, well, that's all of physics. How can we possibly disprove what you're saying? Okay? And so, and the problem is that this is institutional. And I am just going to go ahead and say that at this late stage, it makes sense to me that general relativity was adopted, okay, as a workaround, because it gets predictable results, okay? You can't argue with results. You get the predictions, the equations work. But I think not enough time has been spent trying to think, why is it working? It doesn't make any logical sense. Why does this work? And instead, everybody is just, they multiply dimensions. I mean, dimensions are so promiscuous. They're reproducing like crazy, right? You get string theorists. I mean, they want to go ahead and add even more dimensions to things. And I think that this is just a totally wrong way in which to go. There's 3 spatial dimensions, and time is not a continuum. It's not some kind of dimension of space. That is a ridiculous way of thinking about time, as I've outlined in these talks. And so this all became institutionalized. And what happens is these poor graduate students, they come in, and the only way, if you're a graduate student, and you know what I'm talking about, the only way you advance is you kiss your professor's ass, right? And so you get locked into this, and if you try to go off in any genuinely original direction, you don't get funding if you're a professor, right? And if you're a graduate student, you're not going to get anywhere trying to go off in some original direction. And so, what does this mean long term? It just means everybody gets locked into this type of multi-dimensional thinking where space is deformed in various ways, ad hoc. And anybody who departs from that is treated as if they're ridiculous. I mean, the Mond theorists, I respect Mond because at least these guys in Mond, they're making some attempt to explain it with forces rather than making up dark matter. I still have a problem with Mond because most of them they still respect space stretching, which I disagree with. But at least Mond is making some kind of effort to find out what's really going on here. And so, as I said, several times now, I will say this, that it makes perfect sense to me that general relativity was adopted early on for decades now. It makes sense to me why that was done. It makes sense to me that we still use the equations for predicting outcomes in experiments where, they work, okay? And so that makes sense to me. But conceptually, and I have to say this, conceptually, general relativity as a basis of a cosmology, it is a stupid theory, and only stupid people subscribe to it. Now, when I say that, I mean, obviously we've had absolutely brilliant theorists working on this for decades and decades. So what do I mean by stupid? I mean institutionally stupid. The incentives within the professional ranks of modern cosmology, those incentives are structured so as to reinforce going in this wrong direction. And so everybody is behaving in an institutionally stupid way. And this needs to stop. Okay, we have to give up this general relativity. I don't mean stop using it where it has predictable results. That's not what I mean. I mean, conceptually, we got to start thinking in a different way to investigate things in a different way. And those of you, if you are like some big name donor, and you're paying for this search for dark matter and dark energy, you're throwing your money away. Please find some brilliant graduate students willing to explore alternative gravity. Fund them, please, and give up on this dark matter, dark energy. And so going forward in the Taurus report, I'm going to go in a few different directions now. I think what I would like to do, because I have explained CGC to the limits of my ability, so I'm not going to keep hammering on that. I think going forward, I will just look at different developments as they occur, different research papers as they come out each week, and talk about those, like what's going on in cosmology in general or anything interesting space-related. Also in the future, it may be possible I might go into sort of a live show where people might be able to participate. I'm not sure what I'm going to do, but I've finished that phase of the show where I'm explaining CGC. So thank you very much for watching, and we will see you next week on the Taurus Report, unless I'm sick again. Okay, bye-bye for now.